So what we're going to talk about in this episode is operating systems, why they exist, and we're going to talk about the different components that comprise a modern operating system. It's certainly worth mentioning right now that operating systems are probably some of the most complex pieces of software that exist. That's not an accident. They provide critical services to most, if not all, running programs on a system, and even the programs that don't make explicit use of their services or the mechanisms that they provide would not be able to function were the operating system not there. So you could sort of think of it in a very, very loose way as a software analogy of a CPU, in that the CPU is the only component that executes instructions, and you can think of the operating system as the only piece of software, although it's not technically true, and we'll talk about that, but in a loose way you could say that the OS is the only software component of a system that actually interacts directly with the hardware. And again, we'll talk about a little bit more as we go along about how that may or may not be true. It's not totally relevant for the purposes of this series, but just as an interesting A-side, and I find it interesting. Hopefully you do too, so we'll probably talk about it a little bit. Or I'd certainly allude to it anyway. But nevertheless, moving on. In order to really talk about operating systems and how they exist in their modern incarnation, it's necessary, or it's not necessary, but it's helpful to understand how computers have evolved. And we could go all the way back to computers as they existed in World War II, and then through the 50s and the mainframe eras of the 60s and the 70s, but we are not going to do that. It's not because I don't find it interesting and that I don't think that you might as well, but this would be a whole lot of just talking and reading, and it's already going to be enough of that. So instead what we will do is revisit the page that we used in the overview of a modern computer, and we'll go down here to history, and you could go to history of operating systems, and there is a nice relatively long article going from mainframes and Turing machines all the way to virtualization, which is the direction that things seem to be going in nowadays with modern computing. And it has a synopsis of all that. It's still a nice chunk of text, but there's a whole lot of information here. But specifically, the little bit that we're going to focus on is microcomputers, and what most people think of when you talk about a modern computer is what's sitting on their desktop. And again, for the purposes of this series, that's what we're dealing with. So some of the more pedantic out there may, or not pedantic, but opinionated, might say, oh, well, you're skipping this and skipping that, and yes, I absolutely am. And I'm not talking about embedded systems. We're just going with the generic desktop here. So we'll start, and again, this is just an overview. We're not going to talk about it specifically. We're not going to talk about the history for very long, but it just to provide some context for why operating systems are the way they are and why they are necessary. It's helpful to have this historical context a little bit. So what we will say is that at some point around the 80s, late 70s, early 80s, personal computers and desktops became powerful enough that it was capable of doing more than one thing at once. Which is not to say that it was actually doing more than one thing at once, but prior to this, computers in general had been assigned to single tasks, and mainframes were a way to have powerful computers have the illusion of parallelism of doing more than one thing at the same time. They really don't, or really didn't. And sometime around the early 80s, personal computers and consumer computers were powerful enough to where they started running into the same problem, and they started adopting the solutions of mainframes and basically what we call multitasking. So desktops gained the ability or had enough power to where it was now capable of, had the resources to attempt multiple tasks at the same time. And it's sort of important to note that they're not really doing more than one thing at once. It's just that theirs became so fast that they were able to switch between tasks, and to the end user, it looked like it was doing more than one thing, when in fact it really was not. And so that's sort of a generic definition of multitasking. Running multiple programs in such a rapid fashion so as to appear that they can do multiple things at once. Again, parallelism is sort of a technical term for this. They really were not, but that's more of a technical oddity than it is anything else. For all practical purposes, they could run multiple programs, handle user input, do some background processes, run some services, and maybe do some light networking and things like that. So it became necessary as they gained the power to multitask, or the ability to multitask, one might say, to coordinate the resources of the machine effectively, among other things. But that was sort of my understanding is that was sort of the driving force behind a large piece of operating, or a large chunk of operating system development. How do you manage the resources effectively so that you can accomplish more and more on the same machine, instead of having one program, run from start to finish, and then, okay, well, I'll run this next program from start to finish. What they started doing is allow this program to run for a certain amount of time, stop it or interrupt it, and then go to the next program, allow that to run for a slice of time, and then stop that or interrupt it, and then so on, for however many processes were on that system. And as development in this regard continued, a modern OS came to basically, or not basically, but they came to comprise several components and or services, of which we will delve into now. And so we're going to talk about the different components as listed here in the Wikipedia. We're not necessarily going to read all this text because it's a lot. So instead what we will do is summarize each different piece in brief. But certainly this article here for operating systems on Wikipedia is, if you want to read the whole thing and click on all the links, make sure you have some time on your hands, and because again, these are very complicated pieces of software, some of the most complex that probably exist, and they solve problems in an extremely generic way so as to allow other things to solve specific problems, is how I encapsulate it in my head. So let's talk about the most fundamental piece of the operating system, which is the kernel. Every operating system more or less has a kernel of some kind, and the kernel is basically the lowest level on top of the hardware. It provides facilities and mechanisms for other programs, applications, system software, what have you, to interact with the hardware in the event that it needs to. And in the event that they don't need to interact with the hardware, the kernel abstracts that away, so that other operating system services can interact with it so as to provide a less complicated interface to programs that need to do things like memory management or save files to disk and things like that. The kernel is what provides the mechanisms for most of that, if not all of it, to happen. The next thing that we'll talk about is process management. And so we talked a little bit about this, how you can bring up Task Manager and you have applications and processes and things like that. So you can see it's sort of, we have two processes here that are exchanging, or one's going to the top, one's DWM, and that's probably the reason it keeps bumping up and down is because I'm doing screen capturing, so it's probably capturing, so much memory and then it's flushing it out or handing it off to Cam Studio or something like that. And you have Firefox. And so as we were talking about how operating systems manage the system and allow one process to run and then another process to run, all these processes that we see in this list are live on the system in the sense that they're all running, but every second, every millisecond, I mean, it depends on the system, but there's a specific time slice or quantum or quanta that the processor assigns to different processes. And so whenever that quanta is up, or we're just going to say that time unit because that's a little more accessible of a term, whenever that time unit is up, it switches to, we'll just say it goes from bottom to top. So it starts off running this, and then its time unit is up, and then it goes here, and it executes this, and then it goes here, and then it goes here, and then it goes here. And it's not necessarily linear in the sense that it'll start here and always go here and then go back and forth. Sometimes, or maybe oftentimes, it'll bounce around a lot, but the operating system is what provides process management in the sense of who's getting the access to the CPU and able to execute instructions now, who's getting access to it later, and who's getting access to it next, and it provides an algorithm to determine all this stuff. And scheduling aside, that's sort of a generic term for what we just talked about is process scheduling or just scheduling in general in the context of OSs. And I know there's a link for scheduling somewhere on this article. It also provides facilities for process creation. So say we want to start up Notepad or just calculator. So, I mean, we click here and then the calculator pops up. How does that program even know how to start? Well, that's another mechanism that's provided by the operating system. So it allows programs to become, or to programs to start running by creating processes. And behind the scenes, it's also assigning memory and managing the memory that's associated with each process. So LCD clock here is something that runs on my keyboard. It has 5 megs, almost 6 megs of memory associated with it. How does it know where those 6 megs are? How did it get those 6 megs? Well, the operating system gave it to that process. And there's a whole lot of black magic that goes on in order for that to happen, and that's all provided as a mechanism and what have you by the operating system. Another component of modern operating systems is interrupt management. And interrupt management is a complex topic, one that sort of bleeds the line or blurs the line between hardware and software a little bit. But interrupts basically are rules for responding to events. So I, for one, when I first started learning about interrupts, the easiest, what finally made the light bulb in my head go off was thinking about how, we'll bring up Notepad++. So we want to type something in Notepad or Notepad++. So let's type something on our keyboard. So we hit H. Now, what's the process of that keystroke appearing, being registered by the computer and then appearing in the application? Well, in a nutshell, what happens is when you hit a key on your keyboard, there's an interrupt, and it tells the computer there's an event on this piece of hardware, and the computer goes out, it figures out what that event is, and it through a complex series of events, or a curious series of events, if you're a fan of Lemony Snicket. It says, okay, I know what that event is, and it translates it, and then it comes back to the operating system and says, this is what just happened. The operating system passes that on to the application, in this sense, Notepad++, and it says, okay, the user just hit H, and then they hit E, and then they hit L, or okay, and then equals, but what they really meant to do is hit L, and then O. So, there are 2 kinds of interrupts. It's not, for the purpose of this series, it's not critical that we understand interrupts in an integral way, but nevertheless, we're going over them. There's hardware interrupts or hardware events. We're using the 2 terms synonymously, interchangeably. As we talked about, pressing a key on your keyboard and your mouse is the same way. When you move your mouse, that's generating a hardware event or interrupt, and your operating system is picking up on that, or the hardware is picking up on that event. It's notifying the operating system. The operating system is dealing with it and passing that information on to whatever the relevant application or piece of software is, and it handles and deals with that information or that event accordingly. There are also software interrupts or software events. This is less important, but you might consider it as exceptional conditions. The quintessential example is divide by 0. If you tell a piece of hardware or the CPU to divide by 0, it will trigger that's considered an exceptional condition because you can't divide by 0. So that's another example of an interrupt. So just, again, interrupts are not critical that we understand them, but nevertheless, they're a component of modern operating systems. The next one that we'll talk about is memory management. And by far, memory management is the most relevant to this series out of all the components that we'll talk about in this video or in any future video. We will go pretty far down the rabbit hole of memory management as the series goes on. But for now, what we will say is that an operating system provides multiple abstraction layers so that to programs to facilitate memory allocation and deallocation. So what do we mean by that? Well, programs do, and by memory we're referring to the RAM of the computer. So programs do not know specifically where they are in the RAM of your computer at all. Instead, they are sort of encapsulated, or they are, encapsulated within the operating system, and basically they see a fake view of memory is what we will say. There's obviously specific terms that we will talk about and introduce as the series goes on, but for now what we will say is that the memory that programs any process sees is not the actual real memory of the system. The operating system abstracts that away and makes it so that programs don't need to care about where they are in memory, and that greatly eases application and program development, which developers love, or at least most of them do. And so we will get more into this as it goes on, but suffice to say, it is a critical requirement of any system, modern or legacy, that processes do not disrupt other processes' memory. It is a fundamental requirement for any sort of complexity in the system. And again, memory management is something that we will become intimately familiar with as we go forward. Next, we'll talk about storage management. OSs provide access to hard drives regardless of whether they're mechanical, i.e. magnetic platter drives, or solid state drives or flash drives or whatever. All the storage system and the file system management is provided by the operating system. We'll talk about device driver management a little bit. Most people are familiar with device drivers, and not necessarily in a positive way. So you go out and you buy a new device, you come home, you plug it in your computer, and it says, I don't know how to use this, I need a device driver. You ask yourself, what's a device driver? A device driver is a piece of software that the OS uses to interact with the hardware directly. So the OS provides a standard interface for programs to interact with hardware, and hardware devices are expected to conform to that standard to some extent, such that an operating system is released they're not released every week, contrary to some or whatnot, but that's neither here nor there. So because the operating system release cycle is very slow, an operating system cannot be expected to be updated every time a new piece of hardware comes out. So what is done is, instead, hardware vendors are expected to release drivers that conform to the operating systems that they are supported on. So operating systems provide a generic interface for hardware to interact with the OS, and that is a device driver. And that's why you need a device driver, generally speaking, every time you go buy a new piece of hardware. We will say that device drivers are extremely specific to the device. There is no one-size-fits-all device driver. You'll never say, or maybe not never, but certainly not in my lifetime, will there be a Omni driver that will support everything out of the box, because it would be larger than the operating system itself, probably. Operating systems also provide the networking stack, if you will. Basically, they provide the network protocols that are used to get online, to browse the web, to do all sorts of services, one might say. It's an interesting topic that I find the topic interesting, networking in general and protocols. So I don't want to get too deep into it, but suffice to say, you could probably go here, and a good example. Maybe you could start the protocol stack or something like that. The OSI model is another good, that's sort of lower level than what you might be interested in, but computer networking, maybe this is a place to start as well. Allows computers to exchange data, networking hardware. That's probably 3 decent places to start. But the standard suite of networking is provided, I'm going to close that, is provided by the OS. OSs also do security. So user authentication, restrict access to those who can prove their identity via one authentication mechanism, or maybe 2, or multi-factor authentication, whatever you want to say. Everything we just talked about is pretty much standard in every operating system that's released. It's a little different, whereas each operating system sort of takes its own unique view on certain things, or on certain components. They maybe implement them in a different way, but every modern operating system will provide some set or subset of the components that we just talked about. And they'll also provide a user interface, and we talked about that a little bit. And so, to circle back and say, why do operating systems exist? Because it's impossible for programs and applications to provide all these services for itself. If every application had to provide and come up with all these services and abstractions and manage or memory management and things like that, no one would ever write any programs ever, because it just wouldn't be worth it. And to say nothing of coordinating different programs with each other, if there was no such thing as an OS or some sort of central mechanism that managed these things, then, you know, you'd have one program on your computer and that's it. Because if you ever installed another program, it would probably conflict and your computer would crash. And so the existence of a central mechanism to coordinate the system is sort of organic, or sort of an emergent phenomenon, if you will, just by the complexity of multitasking and the power of modern desktops. In order to fully utilize a system in an efficient way, you need some central authority that governs the resources and says, yes, you can access this, or no, you can't access this right now. And so how is this really relevant to the series as a whole? I think it's important, specifically memory management, process management, and a little bit of the kernel stuff is something that we will deal with in the series as it progresses. Again, definitely memory management, but also it just helps to have a context of what we're operating in. So, you know, as we go forward and we talk more and start using Cheat Engine and actually doing things, certainly not when we first start doing it, but as we get into some of the more advanced stuff and some of the scripting and things like that, we'll start bumping up against the operating system itself and saying, well, you know, we're going to make a call, or we're going to, you know, do something, use a facility directly, you know, that's provided by the operating system. Or say we're talking about how, you know, we'll demonstrate something and we'll do something and we'll say, well, how is this possible? Let's explore how this works and talk about what's really going on behind the scenes. And so when we start doing things like that, we'll make references to all these different components of the operating system. And it just, if we don't have a general idea and an overview of what the different components are and what the function of an OS is, there'll always be this sort of black hole or this black box of, you know, we'll say operating system and we'll talk about it, but it may not necessarily be clear in our heads. So providing this sort of background and context right now will go a long way as we move forward in the series, and just sort of filling in some of the holes that we may not otherwise want to stop what we're doing and say, okay, well, you know, let's talk about process management because now we're attaching the processes. No, let's talk about process management in a general sense now, so that when we go to attach to them and things like that, we can just say, okay, well, you know, here's the process list, and we already know, you know, where are we getting that list? Well, we're getting it from the operating system. Why are we getting it from the operating system? Well, because it manages all processes on the system, because it's basically the gatekeeper for starting a program. So, again, context is important, and normally I would provide links in the description, and I will provide this one operating system one, but I'm not going to go through and extract links from this whole page. I mean, this is where you want to go and just pick your poison, choose your poison, click the link, go down there, or you just scroll all the way down, and there's enough here to keep you busy reading and whatnot for some time, if that's your thing. But with that, we will conclude this, and we will conclude this.